So we've been talking about the Schrodinger equation, and I have the time-dependent Schrodinger equation written out here. And I've put in here, and this has always been implied the whole time, but I've put it in here explicitly that it's dependent, it's a function of space and time. And so we can always just, like I said, it's implied that the wave function, this psi here, is a function of space and time. And so far, I've been using a single dimension of space. And so that gave us a wave function in the form of something like this, where we had A, which is some amplitude, times e to the power of kx minus nu t, where k was our wave number, and that had units that were 1 over meters, and nu was our angular frequency. So angular frequency, looks kind of like a G. And that is 1 over seconds. So that's a frequency. It's angular, so it has radians in it as well, but radians are unitless, and so we can have 1 over seconds here as our units. And then x obviously would have units of m, and nu would have units of time, which is seconds, and so we see that all cancels out there. But anyway, so we know that this is a wave, so this should actually have an I here. I forgot to put that in there, so that should have that I there, the imaginary number. So we know, as I've said in the past, that if we have e to the ix, that is cosine of x plus I sine of x. And so with this, it would just be this e to the I kx minus nu t would be cosine of kx minus nu t plus I sine of kx minus nu t. And so anyway, as I said, this is a one-dimensional version of the wave function here, but we live in the real world, and the real world has at least 3 spatial dimensions, and so we need to expand that out further and add in our y and z dimensions. So this is often written with an r here, which is just the radius. So that's using sort of polar coordinates. But anyway, we can just sort of collapse this x, y, z into this single r here. But this is still so position in space, and so that remains time, because as far as we know, there's only one dimension of time. But this gives us a wave function that looks something like this. We still have the amplitude here, but now we see that our k, instead of just k multiplied by x, we have k dot r. And so in this case, the k and r are actually going to be vectors, because now we can't just say that, so we can't just have our wave like this, where there's just this one direction of space here. Now we need to figure in all 3 dimensions of space, and so we have to use vectors here, because we need to actually say what the direction in space is, rather than just sort of assuming that it is just this one direction of space and using a scalar there. Once again, this should have an I right here. But we have this dot product here, which if you remember your calculus, taking the dot product gives us a scalar as a result of the dot product. So we just have a scalar minus this scalar again. And so what we can do to interpret this, I guess, is thinking about what a wave looks like in 3 dimensions. And what a plane wave looks like in 3 dimensions is, instead of having a single, so if we have our wave like this that looks like this, instead of having a single point that has this value, we now have this value over this plane here, and then a little bit further along in this direction of space, we now have a whole plane that has that value there. So instead of a single spot having that value right there, we have a whole plane that has that value there. So this arrow right here is actually is the vector that's represented by k. I think that's actually usually a lowercase k. So that is this k right here. So that is the k that tells us the direction of propagation of this wave. And the r is position, so that would be position sort of within one of these planes. And as position starting from the origin. So we might say that we have an origin sort of back here. And we know that the direction of propagation is this right here. But now we want some r right here on this plane. So that's going to be the dot product of this. Drew that really bad. So this vector here, which is r, dot product with this vector here, which is k, which is going to give us some value for this spot right here. But we could also think about, so we'll call this r1 and r2. So I'm not good at drawing straight lines, but we can imagine that this is the vector for r2. And if we take the dot product of that with k, we'll actually get the same value here as we got here. And so that value we could, I guess, represent with this arrow right here. The value in this entire plane is going to be the same. So the dot product of k with any r on this plane right here is going to be the same. Then if we move forward onto this next blue plane here, then we get kind of the same thing, that if we take, so maybe we'll call these Q, so we'll call that Q, Q1, and then we could have Q2 down here. So that so the dot product of Q1 with K is going to be the same as the dot product of Q2 with K. So anything on this blue plane here. And you can imagine we could do that for any value in between this first red plane and this first blue plane. We could do that for any value all along this whole propagation here, that if it's on this plane, then it has the same dot product with the propagation vector, which is k right here. And so when we use this in the Schrodinger equation, what you will often see is the Schrodinger equation written something like this. So delta t, or oops, that should be delta psi, and then delta t is equal to, and you will often see this right here, which I mentioned sort of offhand in the previous video. So you will see that there, and then we will have our h bar squared over 2m, and we still need our, so this will be negative, and we still need our I here. And so then this will be applied to this wave function plus the potential here with the wave function. And so this del squared, or Laplacian, as it's often called. So that is so. I guess one interpretation of it is that it's usually the three-dimensional partial differential. So the partial with respect to, or it's actually the second order with respect to x plus that's the second with respect to y plus the partial, the second order partial with respect to z. So that sort of takes into consideration all three spatial directions or dimensions, and so this is what that is, and then we have that acting on our wave function here, and we still have our I h bar over 2m. That should be squared there, and we could add in our potential here. So this is what that this del operator, or Laplacian, is. And I mean, this is, like I said, one way to interpret it is that it's these second order partials operating on this psi. But the other way that is often thought of is as taking the divergence of the gradient. And what that means is, so the gradient is just when you take the first order of x with the first order of y plus the first order with z. So this would give you the gradient of your function here. Then we also take the divergence of that. And so I have some figures up here. So up here is showing the gradient. So the gradient of this function right here, where we see right in the middle we are at 0, and then it increases in all directions. The gradient would be this right here. So the arrows, these vectors, are always pointing in the direction of greatest growth. So you can imagine if you were right here on this, there's some growth if you went this way. It's kind of slowly growing that way or that way, but the greatest growth is going this way. So if we sort of look down at this from the top, we see that there's the greatest growth pointing that way. And a real world sort of place you might have seen this is, you could think of like a temperature gradient. So if we have, well, let's just say we have this room here, and we have some sort of heating element on this side, so that so maybe we have some metal rod here that's letting off heat. You're going to be hotter over here than you are over here. So over here would be colder, and over here would be hotter. So if you wanted to draw a gradient going from lower temperature to higher, you would just draw a bunch of arrows pointing this way. Another place you might have seen it is, well, sort of a way of showing gradient is with a topographical map, where you might see something that looks like this, then like this, and you know that going this way is going up this peak on a mountain, and so we are saying that everywhere on this line is at the same elevation, and then on this line is a different elevation from the first line, but it's all the same elevation. So we could draw that as a gradient sort of going sort of going this way. So with gradients, it's always going from lower to higher, which is why you see on here that since it starts lower here and it gets higher in every direction, our arrows are pointing out in every direction. And I have this here to show that we could have a gradient in 3 dimensions. So you could imagine that there's some value in the center of this sphere that's growing as we go out, and so we can have a gradient going outward. And so then the divergence, though, the divergence is essentially the measurement of how much outward or how much inward there is at a point. And so if you have this outwardness going here, then the divergence would be positive in the middle here, whereas if it is all coming inward, then it's negative here. If at some spot there is no net inwardness or outwardness, then your divergence will be 0. And we can see that we're still using this sort of upside down delta here. So if you remember from your calculus, when we take the gradient, we just put the upside down triangle right there before our function, where if we take the divergence, we actually put a dot in front of it. And so when we use this Laplacian, what we're actually doing is we're taking the dot of this with the gradient of our function. So you first take the gradient and then you take the divergence of that. So we can look up here, if we have this as our gradient sort of moving outward from here, we could see that at the very center here we're going to have a positive divergence because there's a net outwardness. And you could imagine if we looked at a place like maybe right here, we might say that there is a net outwardness too. We have this one arrow coming in and then 2 arrows going out, so there is a net outwardness. And so that is the idea of the divergence of the gradient. And so that is what we are actually doing with this here, with our up here. So this is our Schrodinger equation. Well, this is the one-dimensional version. We are talking about the three-dimensional version. So instead of having this 1 second order partial with respect to x, we would have that Laplacian there acting on our wave function here. And so that's telling us that we want the divergence of the gradient. And if you remember in the previous video, I showed those figures that I took a picture out of the book, where it was something like this, and we saw that there was the inflection points here, and we had the negative up here, so the negative slope up here and the negative up here, and the positive here and here. So we knew that there was sort of a downwardness here and an upwardness here. And so that told us what the shape of this was in one dimension. It told us about sort of the positiveness right here and the negativeness right here. And so that's what the divergence of the gradient is doing, only it's doing it in 3 dimensions rather than in 1 dimension like right here. And so we can say that so for instance, if we have something that's linear, if we have like a linear function like this, then the divergence of the gradient is going to be 0 because it's linear. There's not going to be any divergence. we don't have more upwardness. We don't have any more upwardness right here than we do right here. Whereas if we had something that looked like this, then we have more sort of upwardness right here than we do right here. And so this would be positive divergence. And if we had something that looked maybe more like this, then we have less upwardness right here than we do right here. So that is negative divergence. And so these are the gradients. If we have this linear gradient, then there is zero divergence. If we have this upward gradient, then we have positive divergence. And if we have this sort of plateauing gradient, then we have negative divergence, which means that there is sort of more coming in than there is going out right there. And so that is why the Laplacian, the divergence of the gradient, can give us sort of a 3D picture of what we kind of have going right here, where right here we have this upward gradient that has a positive divergence, you could say, and right here we have a negative divergence, or I might have that the other way around, but anyway, I think the intuition at least should be there that that using this Laplacian operator here, we can actually get the divergence of the gradient, and that tells us about the shape of our wave function in space. And so we can imagine a two-dimensional sort of sine wave like this is going to have, so at this point, say, that no matter which direction you go, you are going to be going down this gradient here, and so we can see from that we would, well, I guess in this instance, at the top of this peak here, the divergence would all be coming inward, because the gradient is always pointing upward. So the divergence here would be negative, and that's what tells us that if we're right here, everywhere we want to move from there is going to be downward, and then sort of the opposite if we are at one of these troughs here, then the gradient is upward in every direction, and so there's all outward there, and so our divergence is going to be positive, where up here our divergence was negative. And so, like I said, that tells us something about the spatial shape of our wave function. Just like in the one-dimensional here, the second order partial with respect to x, which is our space, told us something about the spatial shape of our wave function here. Yeah, so anyway, that is kind of the primary difference here between thinking about it in terms of one dimension and thinking about it in terms of 3 dimensions. And kind of the big change here is, instead of just doing this sort of multiplication of the k and x here, we actually have this scalar product here. And with that, we end up getting this, so that tells us that everywhere in this plane here has the same value when we take the dot product of r with the propagation vector here, k. And so we use this Laplacian here, which so instead of just looking at a single a single dimension. Instead of just taking it with respect to x, we take it with respect uh, to all three dimensions, and that is why we use the Laplacian, which, as I said, is telling us the divergence of the gradient of our wave function. The wave function being this wave in multiple dimensions like this. But anyway, I hope this was enlightening about the difference between one-dimensional and three-dimensional. Um, so most of the time, when you're studying quantum mechanics, you tend to stick with just the one-dimensional version because it's easier to work with. But I just wanted to show here that it does work in three dimensions. It wouldn't be very useful if it didn't work in three dimensions. But anyway, I will see you in another video.